Hi, in this video we are going to see an important application of the modulation property of the Fourier transform, namely amplitude modulation concept, which is maybe the simplest example of a communication system or communication application. Now, let us start with a certain signal. We are going to call this signal an information carrying signal. Now, what do we mean by an information carrying signal? For instance, human speech signal is an example of information carrying signal. It has of course, a certain Fourier transform containing certain frequency components, and all of these frequency components carry a certain information related to the signal. For instance, in human speech signal, male voice will contain lower frequency components as compared to the high frequency content of female voice signal. Suppose that we want to transmit this information carrying signal from a certain point to another point. This is the main problem of telecommunication, meaning communicating from a certain point to another point, to another location, which is quite far away from the original point. Now, for this purpose, we multiply this information carrying signal by a signal. We are going to show this by x sub c of t, and it will be cosine omega ct, and x sub ct is called the carrier. Signal. Now, it will be clear in a minute why we call this the carrier signal. Now, we also have a certain relationship between the frequency content of the information carrying signal and the frequency of the carrier signal as follows. X of t is band limited. That means its Fourier transform is zero outside a certain band of frequencies. So x of omega is non-zero for frequencies, for example, between omega m and minus omega m, and zero otherwise. Therefore, if we plot the magnitude of the Fourier transform of x of t, that means magnitude x of omega, it will have a certain shape like this. Between minus omega m and omega m, it will be non-zero, and it is zero outside this band. For example, in human voice signals, the frequency omega m is in the order of, say, 12 kilohertz or 15 kilohertz, depending on, of course, the person. Outside this band of frequencies, the Fourier transform is 0, and this such a signal is called a band-limited signal. Now, omega c here is chosen much greater than omega m. What is omega c? Omega c is the carrier frequency, and it is chosen by paying attention to the fact that it should be much greater than the highest frequency in the Fourier transform of x of omega, the non-zero highest frequency component. Okay. Now, the transmitted signal, let us call it x t of t, is x t of t equal to x of t cosine omega ct. So it will be the product of x of t and cosine omega ct. So the block diagram of the transmitter will be, we have the information carrying signal x of t. We multiply this is the multiplier, multiply this with xc of t, which is cosine omega ct, and the output is the transmitted signal x t of t. Now this will be fed into an antenna, and it will be transmitted as an electromagnetic wave. Xt of t is transmitted as an electromagnetic wave. Okay, so this is the transmitter configuration. Now, in order to understand why we are performing such a multiplication of the information carrying signal with the carrier signal, let us look at the Fourier transform of the transmitted signal. Now, Fourier transform of the transmitted signal is capital X t of omega, and this will be equal to, now since the transmitted signal is the product of two signals, remember we have the multiplication property or modulation property of the Fourier transform. So we will have 1 over 2 pi x of omega, the Fourier transform of our information carrying signal, convolved with the Fourier transform of the carrier signal, which is pi delta of omega minus omega c plus pi delta of omega plus omega c. So the Fourier transform of the transmitted signal is 1 over 2 x of omega minus omega c plus 1 over 2 x of omega plus omega c. In other words, all the frequency components of x of t are shifted to the higher frequency omega c or minus omega c. Okay. Therefore, we have this result. Now, why do we perform this multiplication in time domain, or equivalently, the frequency shift operation in frequency domain? Because we want to transmit the signal, and in order to transmit the signal, we need an antenna. Now, in antenna theory, it is well known that antennas are resonating structures. Therefore, their physical size must be comparable to the wavelength. Now, therefore, you choose your carrier frequency omega c such that the corresponding wavelength to that frequency must yield a feasible wavelength, in the sense that we are going to have an antenna with a feasible physical size. For example, if omega c, or rather let us talk about the frequency in hertz, if we choose our carrier frequency in hertz as 1 gigahertz, the wavelength corresponding to 1 gigahertz is 30 centimeters. Therefore, an antenna size comparable to 30 centimeters, say between 10 centimeters up to 30 centimeters, will be okay for our purposes, especially when we are considering the receiver side, because there will be maybe one transmitter, but there will be several receivers, so the constraints on receiver antennas are much more important. So the reason behind this multiplication operation of the information carrying signal with a carrier wave is related to a practical aspect of the problem, namely the antenna size. Okay. So after this operation of multiplication, which is called modulation, and it is called amplitude modulation, because when you multiply the information carrying signal with the cosine signal, and the cosine signal has a frequency omega c, which is much larger than the highest frequency in the Fourier transform of x of t, it will seem like a signal which is modulated by means of this carrier signal. Its amplitude will be the envelope of the signal after the multiplication operation. Now, after transmission, we are going to receive the signal on the receiver side. So, how do we obtain the signal back? So, that will be our next problem. So, let us look at that problem next. Okay, on the receiver side, the received signal is, in fact, it is the transmitted signal, but due to the propagation losses, there will be a multiplier. So xr of t will be alpha x t of t. And alpha will be a constant introduce for transmission losses. Okay, because the antenna, although the antenna can be directive and it will direct the signal in a certain direction, still most of the transmitted signal will be lost in free space. It will be transmitted in other directions. So all of these are called transmission losses. Therefore, we need a constant to represent such transmission losses. So xr of t will be therefore equal to alpha x of t cosine omega c t. Now, the question is, how can we obtain the information carrying signal back? So, how can we extract x of t from this signal? This is, of course, an important problem. Now, the answer is very elegant and simple. We just multiply the received signal once more with the carrier signal. So, obtain the signal. Let us call this new signal y of t as y of t equal to xr of t cosine omega c t. In other words, it will be equal to alpha x of t cosine square omega c t. But we know that cosine square t is just 1 over 2 plus 1 over 2 cosine 2 omega c t. Again, in frequency domain, we will have y of omega equal to alpha over 2 x of omega plus alpha over 2 x of omega convolved with pi. We will have also a 2 pi coming from the modulation property, so let us also consider that. Well, let me write it over here. In frequency domain, okay, y of omega will be equal to alpha over 2 x of omega plus 1 over 2 pi coming from the modulation property. And we also have alpha over 2 as a multiplier. Then we have x of omega convolved with pi delta of omega minus omega 2 omega c now, because we have a frequency shift to 2 omega c plus pi delta of omega plus 2 omega c. Okay. So we have y of omega equal to alpha over 2 x of omega plus, okay, pi's will cancel out. We will have alpha over 4 x of omega minus 2 omega c and alpha over 4 x of omega plus 2 omega c. Okay. So if we plot y of omega, magnitude of y of omega, of course it will also have a certain phase, but let us just plot magnitude of y of omega. So this is magnitude of y of omega. So we have minus omega c, these omega c is the carrier frequency, and then we have 2 omega c and minus 2 omega c. Therefore, we are going to have such a graph. Okay. X of omega, in fact, if we forget about the constant multipliers, which are not very critical, we have x of omega, and x of omega shifted to 2 omega c and minus 2 omega c. So how can we obtain x of t or x of omega? Just by low-pass filtering. To get rid of the frequency components centered around 2 omega c and minus 2 omega c, we can use an ideal low-pass filter with a frequency slightly greater than omega m, with a cutoff frequency slightly greater than omega m. We can extract x of t. So we can use an ideal low-pass filter to obtain x of t. The cutoff frequency of the filter must be slightly greater than omega m. And remember, omega m is the highest frequency component in the information carrying signal x of t. So this is the amplitude modulation system, which is the simplest example of a communication system. Now, in order to be able to transmit the signal, first we multiply the information carrying signal with a carrier signal and then transmit it. And on the receiver side, we multiply the received signal once more with the carrier signal, cosine omega ct, and then use an ideal low-pass filter to extract x of t, to get rid of the frequency components around 2 omega c and minus 2 omega c. Okay, maybe we can just finally summarize the amplitude modulation and amplitude demodulation systems in terms of block diagrams. So let us now do that. So if we just summarize what we have seen in this video in terms of the transmitter and receiver block diagrams. So we have the signal, information carrying signal x of t, and it is multiplied by the carrier wave or carrier signal xc of t, which is equal to cosine omega ct, and then this signal is transmitted by the transmitter antenna. So this is the transmitted signal x t of t. Okay, so this is the receiver, transmitter configuration. Okay, so the transmitted signal is launched as an electromagnetic wave, and this electromagnetic wave on the receiver side is received by the receiver antenna. So we have the received signal xr of t. Okay. Remember, the received signal is the transmitted signal multiplied by a certain constant which accounts for the transmission losses. And the received signal will be next multiplied by again the cosine signal, the carrier signal, cosine omega ct once more, and we obtain the signal y of t. And y of t will be fed to an ideal low-pass filter. Okay, so this is the ideal low-pass filter, and the frequency response of the ideal low-pass filter will be, let us show it by h of omega. It will be equal to a constant. It can be chosen arbitrarily if you wish, but the cutoff frequency is chosen. We have shown the carrier frequency also by the symbol omega c, so I cannot here use the symbol omega c for the cutoff frequency. So we can choose, for example, this as omega cap and minus omega cap. And omega cap is greater than omega m, slightly greater than omega m, just to be able to capture all the information related to the signal x of t, and therefore the output will be x of t, or as constant multiplied by x of t. But the important point is that we are able to extract the information carrying signal from the by using the received signal. We are able to extract the information carrying signal. Okay, therefore this is the receiver configuration on the receiver side, and the operation we have performed during transmission is called amplitude modulation, because we multiply the information carrying signal with the carrier signal, and therefore the original signal x of t acts as the envelope of the signal after this multiplication operation. And on the receiver side, we have the so-called amplitude demodulation. Operation, which is composed of the multiplication by the carrier wave once more, and then applying the low pass, ideal low pass filter. Okay, thanks for watching.